Hello, Mr. Claudia here, and today we're going to start off a chapter on sequence and series. Now I know you've done sequence and series before. In your grade 10 year, you had an ISU on sequence and series, but who really learns anything from ISUs anyways? As it is, it's grade 12 now, we're getting ready for the IB exam, and sequences and series are definitely part of it. So this video is meant as both a refresher and a way to make sure you haven't missed anything from that chapter. So you might be able to go through it quicker than other chapters, but we'll kind of go through the full lesson here. So what's a sequence? Well, a sequence is a list of numbers written in a defined order following a specific rule. Sequences are cool, and we don't really do a lot of sequences in our high school math career. We only really focus on a few of them. But there are whole departments in universities that look at different sequences. Now we can have either a finite sequence, which is made up of a fixed number of terms, or an infinite sequence, which obviously goes on forever. So let's start talking sequences. So if I want a finite sequence, I could look at any sequence. So 2, 3, 5, 7, 11, 13, 17, 19. Any idea what that sequence is? Those are all prime numbers. Now, the prime numbers obviously is an infinite sequence, but in this case, I've written it as a finite sequence, so the prime number is less than 20, say. So this is the prime numbers less than 20. An infinite sequence is obviously a sequence that goes on forever. Let me write an infinite sequence for you. For example, 0, 1, 4, 9, 16, 25, and then I have the ... to show that the sequence goes on forever. Any idea what that sequence is? That's the square numbers sequence. And those are all numbers where basically each number is a square of an integer. So 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, etc. Now when we write sequences, yes, we often write them as this with the commas and then the ... to show it's infinite. And we label each of these, we define them in terms of terms. So this would be term 1 and we call it U1. This would be U2, U3, U4, U5, U6. So when you see U, the U is referring to the term number. Okay, now usually what we do is we try to define a general term. That is kind of like a general expression that allows us to write out the entire sequence. And we're going to be doing that in this chapter for two common sequences. So for example, I could write un equals n plus 2. That's a general term, and I could use this now to write the sequence out. So when n is equal to 1, I end up with 3. Then, when n is equal to 2, I end up with 4. When n is equal to 3, I end up with 5. And you get the point, right? It keeps going. That's an arithmetic sequence. That's what we're going to be looking at today. Another example is if I had a general term and it was, say, 2 to the power of n. For this sequence, it would start with, 2 to the power of 1, which is 2, 2 to the power of 2, which is 4, 2 to the power of 3, which is 8, 2 to the power of 4, which is 16. So instead of going up by a fixed amount each time, it's actually going out, it's doubling each time. This is a geometric sequence, which we're also going to be looking at in this chapter. However, it is worth noting that we can also define, not all sequences can be defined so easily with a general term, and again, there are many different types of sequences. We can also define sequences recursively, and that is where you use previous terms to help define it. A good example of this would be the Fibonacci sequence, which we have talked about in this course, which we would say each term is the sum of two previous terms. So without dwelling on it too much, the Fibonacci sequence starts with 0 and 1, and then to find the next term, you add the previous two terms. So 0 and 1, which is 1. Then to find the next term, you add the 1 and 1, so you get 2, 1, 1, 1 and 2, you get 3, 2 and 3, you get 5, 3 and 5, you get 8, and then 13, and that's the Fibonacci sequence. It's a neat one. It's got lots of effects in nature that we see, and kind of you see it when, for example, in a tree growing. If you count the number of trees at each level, they often tend to grow following the Fibonacci sequence. If I wanted to write this recursively, well then un, that is my general term, which I had, like I defined before, this is made up of taking the previous term, which is un minus 1, and adding the term before that, so un minus 2. So this is the general term. This is the previous term. And this is the two previous term. So if I wanted to find, say, the fifth term, u5 would be u4 plus u3. So that's a recursive definition. We're not really going to use this much more. We're going to be focusing on these two sequences, arithmetic and geometric. However, let's do one more kind of fun sequence, because we're not going to do many more fun sequences in this chapter. Here I have, can you write a recursive formula for the number of dots here? These are actually, this is called triangular numbers. You've learned square numbers, now you've learned triangular numbers. So the first term we have 1, then we have 3, then we have 1, 2, 3, 4, 6, plus another 4, which is 10, plus another 5, which is 15. So this would be, this is U1, U2, U3, U4, and U5. Okay, so if I wanted to write a sequence for a recursive formula for the number of dots here, well, okay, what's happening each time? When I go from here to here, I'm adding 2, then here to here, I'm adding 3, and here to here, I'm adding 4, and here to here, I'm adding 5. So I kind of see the pattern here. Again, this is really different than the kind of things we're going to be learning in this chapter, but this is a sequence we should be able to figure out. So basically, like to find U3, for example, or sorry, U2, which is 3, I'm taking the previous term and I'm adding 2. To find the third term, I'm taking the previous term, I'm adding 3. So I would say that my sequence, un, is equal to the previous term plus whatever the term number is. And we should define the first term, which is u1 is equal to 1. So if you wanted to test this out, u6 would be equal to u5 plus 6. And that would give me 15 plus 6, which gives me 21. So you'll see if you ever do a math contest, they'll often give you questions that involve sequences and weird sequences, where it really is testing your thinking skills, right? A question like this is more about thinking and looking for patterns. That's a little different than the algebra you've gotten used to in your high school math courses. But like I said, because this is a high school math course, we're going to be focusing on these two sequences and the math that goes with them and the algebra that goes with them. So let's start. Let's get to it. The arithmetic sequences. It's not arithmetic sequence, it's arithmetic sequence. You also might see it called an arithmetic progression. So that's an IB term where they use in other parts of the world. This is a sequence in which each term differs from the previous one by the same fixed number. Let's consider an example here to help you kind of understand it. So we have a restaurant which is trying to figure out how many people they can fit at their tables. One table sits 4 people. If they push the 2 tables together, they can fit 6 people. If they have 3 tables together, they can fit 8. So how many people would they be able to sit if they push together 20 tables? Okay, so let's consider this sequence. So we have a table 1, or let's say there's one table, sorry. And what did they say? There's 4 people. Okay, if I have 2 tables, I have 6 people. If I have 3 tables, I have 8 people. You know that feeling where you're doing a sequence, you're like, I don't know if I'm going to get this sequence. Well, I think I understand what's happening with this sequence. It's not something I'm going to have difficulty getting. Each time I add a table, it goes up by 2, right? This one is 10, and it would go on and on probably, right? So I put dot, 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 dot. Now they want to know, we'll get to that later. Okay, so in terms of what we're calling this, well, let's call this U1, right? That's kind of how we label sequences. This is U2, U3, U4, etc. Hopefully we squeeze all this in. So what you want to do is figure out, well, how much is it going up each time? Now, for us, it's pretty simple to figure that out. I would just subtract, right? 6 minus 4, or I can just look at it and say it's 2. But just so that we have a strategy for doing this each time, to find the difference, I would take U2, subtract U1, which is 6 subtract 4, and that is equal to 2. So my difference, the amount that goes up each time, is 2. I can test it over here. It should be the exact same. This would be U3 minus U2, which is equal to 8 minus 6, which is equal to 2. So I can see, and I won't even do it here. I'll just kind of put a plus 2. But I can make a note that the common difference is found by subtracting term minus the previous term. Previous term. And in other words, we would say each additional table increases the seating by 2. Oops, there we go. So you guys kind of got a sense looking at this question. Each extra table increases that the number of seats by 2. But the way you can kind of officially do that is by subtracting one term from the previous, or the previous term from the term you're looking at. So now, what the question was asking for were, well, what's going to be the deal with 20 tables, also known as U20? Unfortunately, we have very poor space management here, but to figure out U20, well, I'm going to start with, basically I need to add 2 to the number 4. To get to 3 tables, I had to add 2 twice. To get to 4 tables, I had to add 2 3 times. So to get to 20 tables, I have to take 4, and I have to add 2 times 19, right? 19 extra additions of 2. So if you want to think about it, this is table 1. This is the common difference. And this is the additional tables. You could do that in your head. 2 times 19 is 38, so this gives you 42 seats. And that is a arithmetic sequence. The one little note we'll make here is this is kind of a linear thing, right? Like, if anything, the sequence and series chapter links up a lot of things we've already learned in the course. Arithmetic sequences are related to linear equations, right? This looks like a linear equation, and it really is. It's a discrete linear pattern. So, sorry about the space, but that's kind of our introduction to arithmetic sequences. Let's tourner la page. Okay, so what we're going to do is define the general term. Remember, the general term is an equation that allows you to calculate any term in the sequence. And we basically just found it out. The general term is u sub n, so the general term is equal to the first term, u1, plus n minus 1, the number of the term, subtract 1, times d, the common difference. So there, un, u1, n, and d. This formula, actually all the formulas we're going to do in this chapter are all on your formula sheet. So there is an element of plug and chug to the sequence and series chapter. If you're, kind of organized about it, you should just be able to apply these formulas and successfully do most of the questions that you'll see. Let's try doing just that. Let's start with this example 1. Consider this sequence. A7, A3, 79. Okay. Find the formula for the general term. Well, I'll just write it out again here. One good strategy when we're looking at sequences and series is to figure out, is it, that common difference. So if I subtract 83 minus 87, again, I can do that. I can show the work, even though it's pretty clear to me this is going down by 4. And I can check they're all going down by 4. That's a useful check to do, right? To figure out what sequence you're looking at. So now I know that d is equal to -4. We're going to have a hard time filling all these questions in. D is equal to -4. We also know, okay, so then I can write the general term for the sequence, which is un is equal to, okay, so it was the first term, which is 87, plus n minus 1. Remember, this is a general term, so we don't know what number we're talking about. It could be any term. So n we keep in the formula, and then we have -4 here. Now, I will just clean it up because it's a little messy, so, or it could be better, right? So this is -4, right? You have to distribute this -4 to both of these terms. Just watch your negatives. So -4n plus 4. So I end up with 91 minus 4n, right? And as I told you, this looks linear, right? And an arithmetic series is very much related to the linear expression. Okay, so now I have an expression that will allow me to find any term. First term, I would just sub in n equals 1. To find the second term, I would sub in n equals 2. Part B, to find the 40th term, we sub in n equals 40. So I end up with u sub 40 is equal to 91 minus 4 times 40. That's what, 8160 minus 90, 7069. 91 minus 4 times 40, -69. Good. Okay, and part C, how many terms are in the sequence? What do you mean, how many terms? Oh yeah, look, the sequence ends. It doesn't go on forever. So number 297 is the last term. Well, what term number is that? Well, to figure that out, I'm going to sub in un is equal to 297. So I end up with -297 is equal to 91 minus 4n. I'm going to bring the 91 to the other side, so I end up with 297 minus 91. So I get 297 plus 91. I get -388 is equal to -4n divided by 4 is 97. Does that number make sense? The 97th term? Well, the number, it keeps going down, 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 down quite a bit. So yeah, it makes sense. It would be about 100 terms in. So we see that the sequence and series, you really can lean on the formula, and there's a little bit of understanding required. But really, at this point, we're just dealing with linear algebra. Okay, let's do a slightly more difficult example. Find the general term un for an arithmetic sequence with u3 equals 8 and u8, it should be -17. Just made that correction. So we don't really know much about the sequence. We don't know where it starts. We don't know what the common difference is. But if I write out what I know, which is, okay, the number 8 that's U3. And then U4, okay, well U4 we don't know, U5 we don't know, U6 we don't know, U7, U8 we know, which is negative 17. So I know something's happening here. It's going down by a certain amount each time, but I don't know what it's going down by. But what I could do is, okay, well I know there's a common difference here, right? Some common difference is being added to U3. I mean, it's a negative common difference, but something's being added to 8 to get to this term. Then I have to do it again because we've been told in the question that it's an arithmetic sequence, right? So we know that it's a common amount that's being added each time. So it's the same. D is always the same. So a neat kind of thing that we actually know is that U3 plus 1, 2, 3, 4, 5 of those common differences should give me U8. Now U3 is 8, 5D, and U8 is negative 17. So I should be able to solve this now. Subtract 8 from both sides. I get 5D is equal to negative 25. So I get D is equal to negative 5. Okay, so now I know the common difference. So to use the formula though for the general term, I need to know the first term. And unfortunately I don't have that, right? I only have U3. So I have to kind of think backwards to U2, U1. So you can almost reason this out the exact same way, right? You can think, so what is the first term? Well, it would be U1 is equal to U3 minus D minus D, so minus 2Ds. So I end up with 8 minus 2 times negative 5, or in other words, 8 plus 10, which is going to give me 18. Does this make sense? So if I started with 18, I subtract 5, I go down to 13, subtract 5, I go down to 8. So yeah, that does make sense. So now I know the first term, I know the common difference. So now to write my general sequence, general term, it's UN is equal to the first term, 18, plus n minus 1 times negative 5. Now that's a little messy. I'm going to try to fix that up. So it's 18 minus 5n plus 5. So that gives me 23 minus 5n. And that's my general term for that more difficult question. Okay, and the final example, the quote-unquote hard example. You have, okay, 3 terms, 3k plus 1, k, and negative 3. These are consecutive terms in an arithmetic sequence. Again, arithmetic sequence is a useful thing to know here because it tells me that there's a common difference each time. So I have the term 3k plus 1, then I have the term k, and then I have the term negative 3. And you have to think it goes on in all directions. So now, because these are consecutive, I know that going from this term to this term, I go up by a common difference. This term to this term, I go up by a common difference. Okay, well, I can go back to that idea of how to calculate the common difference. Remember I said at the beginning, I just take this term and subtract this term. It always seemed really easy, but it's useful now, right, to remember. Well, the common difference is equal to k minus the previous term. So that is going to give me k minus 3k minus 1. So I end up with negative 2k minus 1. And then for this second expression, common difference, it's going to be the same thing, negative 3 minus k. Now, you have 2 expressions and 2 unknowns. So I can, this is my first expression here. This is my second expression. To solve a system of 2 equations, 2 unknowns, we use substitution. Okay, so I have equation 1 is equal to equation 2. I end up with negative 2k minus 1 is equal to negative 3 minus k. So then I'm going to bring negative 1 to the other side, so that gives me negative 2. I'm going to bring k to the other side, So it gives me negative k. So I end up with k is equal to 2. And I think that's what the question was looking for, find k. So there's a little bit of thinking in that question there. So that's our first section on arithmetic sequences. Again, it's probably mostly review for you. And like I said, it's mostly using the formulas effectively and thinking a little bit. Nonetheless, here's some homework. Page 164, number 1 to 6. Page 166, number 1 to 2. 167, number 1 to 4. Now, if you're not going to do all of that, do the last page, 167. Those questions are challenging and are a really good refresher to the whole thing. If you find that they're difficult, then you might want to revisit some of the easier ones. Okay, good luck with that, and we'll see you next time.